Bismillahirrahmanirrahim. My name is Muhammad Bilal, and I'm going to discuss here a research paper written by Zhojing Yong and its group. And the topic name is a chromatographic method for the separation of tungsten from the silicate sample for high precision isotope analysis using negative thermal ionization mass spectrometry. And this research paper is published at the 31st of July 2020. The first thing we are going to discuss here is the abstract. A new chromatographic method for the isolation of tungsten from the large mass of silicate sample that contains more than 1 gram for the ultra high precision isotopic analysis was developed. The purification of tungsten was achieved through two stages of rapid chromatographic separation. In the first one, titanium, zirconium, hafnium, and tungsten were separated collectively from the sample matrix through a column named AG1X8, and that is with the 10 ml resin volume and has 100 to 200 meshes. So we are going to discuss it later in this section. So moving next, and then the and the tungsten was separated from the titanium by using 0.6 ml of TODGA resin column, and it can also be separated from the zirconium and hafnium by using 0.3 ml TODGA resin, whose particle size is 50 to 100 micrometer respectively. The total yield of tungsten along with the an exchanger and TODGA chromatographic separation step is more than 90%. So overall, a lot of amount, a lot of amount of tungsten is obtained through this. And next, there are two main methods for tungsten isotopic analysis. The first one is negative thermal ionization mass spectrometry, anti-IMS, and multi-collector inductively coupled plasma mass spectrometry. The first one is anti-IMS technique. In this, the tungsten is analyzed as WO tungsten oxides, 3 minus in complex isobaric oxide correlation are required to get tungsten isotopic ratio from the measured tungsten oxide ion beam intensity. So after that, particular with in run measure oxygen isobaric ratio from the isobaric oxide correction, high precision analysis of the vanadium isotope 182 over the 184 ratio with the long-term reproducibility of less than 5 ppm has been achieved. So in the next, the that is the MCICP MS technique, that is better than the previous one and have 5 to 6 ppm external precision, and that can be achieved through this, provided that vanadium positive ion tungsten positive ion beams are strong enough. For the ultra purity, it is required to extract a lot amount of high purity vanadium for large masses of sample matrix, uh, whose weight must be greater than 1 gram. So the next section is about the experimental section. In this, we are going to discuss the reagents, columns, and the lab years. So the reagents are HCl, HF, and HNO3, which are further purified by subboiling distillation. And the ultra pure water are also applied for the lab years, washing and dilution of the reagents. And the HClO4, that is about 70% volume and 99.99% trace elemental basis, and H2O2, that is about 30% volume were used without any additional purification. No need of purification is required when we are using HClO4 and H2O2 reagents. So, the ion exchanger resin column used for the separation of the four of the elements titanium, zirconium, hafnium, and tungsten from the sample matrix. As the sample matrix contain a lot of elements, but we have to filter out these first, and then the tungsten. So all these are separated from the sample matrix by using bio red econo pack chromatographic column that is about 1.5 centimeter, and its packing is 10 ml of bio red ag1 x8 100 to 200 form resin mesh chloride form resin. The TODGA column used for the separation of titanium and zirconium hafnium from the vanadium was produced as follows. So first 10 gram of unbranched DGA with the particle size of 50 to 100 micrometer was soaked in 50 ml, about 2 molar HNO3 and as sonicated in ultrasonic bath for at least 30 minutes. Then resin was suspended in about 2 molar HNO3 for the more than 1 week. And then the slurry resin was then packed into bio red polyprep empty column with 10 ml reservoir. Finally, the resin bed volume was set to 0.6 ml or zero point 0.3 ml. Medium porous polyethylene freight material was set onto the top of resin for the bed support, and the lavware used include uh, 5, 15, 30 or 60 ml PFA Teflon vials with the screw top layers. So all were about the reagents, columns, and the lavwares. And the next one is we are going to discuss the sample dissolution, how the sample is going to be dissolved. So first, approximately 1 gram of GS JIB3 and 2 gram of US GS BHVO2 powder were dissolved in 30 ml Sevelex Teflon beaker using 20 ml 22 molar HF and 5 ml 15 molar HNO3 on a hot plate at about 180 degrees centigrade for 1 week, and it really requires time. So then we have to dry it down at about 150 degrees centigrade. After all, the resulting fluoride is digested by 2 times with the 10 ml 15 molar HNO3 and zero point 0.5 molar 30% H2O2 volume by volume at 180 degrees centigrade. So we have to maintain 180 degrees centigrade again for overnight. So the samples were dried down between each treatments. Next, the sample were converted to the chloride by 2 times of resolution. So the whole sample will be converted into the chlorides at 150 centigrade. We have to lower down the temperature in 10 ml 6 molar HCl drying down. After it, 15 ml of zero point 0.5 HCl and zero point 0.5 molar HF are to be added in the results and are again heated up to the 180 degree centigrade for at least a day, 24 hours. So the sample were centrifuged and supernatant were transferred into a Teflon beaker. Then treated, we have to treat it with 5 ml of zero point 0.5 molar HCl and zero point 0.5 molar HF using ultrasonication and centrifugation. So the secondary supernatants were combined with the former supernatants for the ion exchanger chromatography. So the next is about the cautions. We have to the most important part, that is about the cautions we have to prepare for this caution. And the cautions are: number one, when the sample mass of the basaltic rock powder is more than 1 gram, the reaction is violent. So when HF is added, the mm, the acid should be added, slowly with the great care. It should not be, just putting it in a certain way. It might get be dangerous for you as well as for the others working in the lab. So the next thing is, we have to, for digestion steps, when we are going to, adding HNO3 and H2O2 digestion step, it is necessary to add about 10 ml of HNO3 first, and then zero point 0.5 ml H2O2. Not going to, put into the in a just abrupt way, but putting it just the necessary amount of HNO3 and H2O2. After the sample results from the former steps was fully cooled down, we have to wait for the cool down of the first step, and then moving to the next step. Otherwise the reaction would be violent, and it could be really really dangerous for you and for the others too. So the next is the chemical separation, and in this we are going to discuss the separation of uh, titanium, zirconium, hafnium, and tungsten from the sample matrix by anion exchange chromatographic. And the first at first the whole mixture was separated collectively from the sample matrix by an ion exchange scheme as presented in the table 1. So here is the table 1, and we are going to discuss the whole in the next slide. And that is and we are going to discuss in that we have to, sort out different chemicals, different elements first, and then the add by using, 7 molar HCl and 2 molar HF. Volume is 20 into 5, and this we have to do first the resin cleaning, and then the equilibration is done with the zero point 0.5 ml HCl and zero point 0.5 ml HF solution, and the volume is 10 into 10, 10 plus 10. And then we do the loading process. That is done with the zero point 0.5 molar HCl, zero point 0.5 molar HF. Volume is 20 ml. And then arranging the matrix element, that are iron, calcium, magnesium, aluminum, and sodium, potassium, chromium, etc. All the other elements are arranged down after the whole process that I have discussed above. And all these elements are arranged down by using 0.5 ml HCl and using zero point 0.5 molar HF solution containing the volume 10 into 3 ml. So we are left with the titanium and zirconium, hafnium, and tungsten. So for their elution, we have to add 7 molar HCl uh, and 2 molar HF solution containing the 20 into 3 volume. So this will elute all the remaining 4 elements, that are titanium, zirconium, hafnium, and tungsten in that mixture. So here is the overall detail that I have mentioned in the previous uh, slide. So after all the first table, we are moving to the second table. The second table is to separate, as in the first step we have separated the mixture of titanium, zirconium, hafnium, and tungsten from the all other elements present in the mixture. So in the next we are going to separate the titanium and vanadium. and zirconium hafnium by TODGA extraction chromatography. So the first step of TOTGA column separation scheme is given in the table 2A, that is given in the next slide, and we are going to discuss it here upon. The first is TOTGA column packed with the 0.6 ml TOTGA resin were pre-cleaned 4 times with the 5 ml 3 molar HNO3 1 molar HF, and then conditioned twice, and then we have to condition it with the twice amount with the 5 ml 8 molar HCl and 0.01 molar HF. After that, the fractions of titanium, zirconium, hafnium, and tungsten fractions will be collected from the first column and dried down and can be digested with the mixture of 3.5 ml HCl, HNO3, and H2O2 in a ratio 1 to and 0.5. And that is and the purpose of using this mixture is to destroy the whole organic compounds in that mixture and then digest it with the 0.5 ml 22 molar HF solution. So at last the sample results was redissolved with the 5 ml 8 molar HCl and 0.01 molar HF at 180 degrees centigrade overnight. We have to heat it again at 180 degrees centigrade for 24 hours. Okay, and here is the overview of table 2, and in the first section we have already discussed that we have to done different procedures from the 2A section. And the first procedure we have to do is rinse, cleaning, and then equilibration, then loading the sample, and then rinse the titanium, and titanium will be rinsed down, and then the tungsten will be eluted. After the tungsten elution, the hafnium and zirconium will be also be eluted out by using different eluents that are mentioned in the left upper corner for the respective procedures. And if we talk about the section B, table 2B, in which we are going to further purify the tungsten by biorad polyprep column packed with the 0.3 ml 50 to 100 micrometer TODG resin. So in this again we are going to rinse going for the rinse cleaning by using eluents 3 molar HNO3 and 1 molar HF, and the elution is 5 into 3 ml, and next is the equilibration, loading the sample, elute the residual amount, and finally we will get the vanadium the most, or sorry, a tungsten the most. And for all these we have to use different eluents that are given in the left lower corner: 3.3 molar HNO3, 1 molar HF, 8 molar HCl, 0.01 molar HF for the liberation, and again for the load sample, and again for the eluent reservoir, and finally 3 molar HNO3 and 1 molar HF solution containing 2.5 into 2 volume for the tungsten collection. So here is the overall procedure that I have discussed in the previous slide about the table 2 A and B, and it is going on. So after the table 2 we have LET dot tungsten. In the table 3 we are going to discuss here after the evaporation the results were digested with the 50 to 100 microliter of HClO on a hot plate at 2. So we have to heat this up to 210 degrees centigrade twice times, and this will burn off the organic matters from the resin. So in this we have to burn it down at 210 degrees centigrade, and the purpose of this burning is to burn off all the organic matters from the resin. Finally, the results that will be dissolved by using a zero point 0.5 molar 3 sorry 0.5 ml 3 molar HNO3 and 1 molar HF solution, and this will be held in the 5 ml Civilix conical Teflon beaker, and this will be dried to the dryness for the anti-IMS analysis. And here is the overview of the table 3, in which Faraday's cup configuration for the measure of tungsten isotope by the Triton plus times. In short, the table 3 depicts that the purified uh, tungsten analyte was loaded onto a zone refined high purity single RE filament and a solution containing lanthanum and indium was used as a ionization enhancer for the anti-IMS uh, tungsten isotopic analysis. So tungsten isotopes were measured as their oxides using multi-static analytical protocol with 2 lines of acquisition as listed in the table 3, as there are 2 lines. So all the Faraday's cups were electronically connected to the amplifier with the 1011 ohms resistance, that is quite uh, high. And next, in order to obtain perfect peak alignment for the 2 lines of data acquisition, the dispersion parameter for the zoom system were set to 0 volt for line and 4 volt for the line 2, and that is also given in the table 3. So with the analytical protocol, all vanadium oxides and indium oxide species, as well as 180 vanadium isotope were measured. No pressure in the ion source chamber and no significant effect on the vanadium oxides negative ion beam intensity. Next, the tungsten isotopic measurements were typically run at 1350 to 1400 degrees centigrade. That is really high temperature for this, and we have to done this on this temperature. With the 184 vanadium oxide isotope, whose mass is about 232 ion beam, with the intensity which is going to be released is 1 to 1.5 volt, and then 185 Re oxide signal usually drops to the less than 50 ml volt at the run condition of tungsten. The data acquisition was subdivided into blocks with 20 integration per block. Uh, Between the blocks, baseline measurements ions being refocusing as well as peak centering for both the mass steps were conducted. During each measurement, the ion beam intensity were maintained to the 80 to 120% relative to the ion current set at the start of the run. Generally, 800 to 1000 cycles of the data were acquired depending upon the sample size, and one sample analysis took about 8 to 10 hours for the completion. The oxide interference correction were performed using an run measured oxygen isotopic ratio, because very small 186 vanadium oxides signals was impacted by interference of 187 vanadium oxide ions, and the ratio 170 to 160 cannot be precisely measured in that run. Instead, we use a linear oxygen mass fractionation line obtained from the anti-IMS uh, isotope analysis in our laboratory. 34 was used to calculate uh, the in-run 170 to 160 ratio from in-run measured 180 to 160. So here is the overall scenario, and we get the final results, that are about 0.9276 using the exponential law. And during the calculation of the dilution curve and yield the test, the elemental concentration were determined by inductively coupled plasma spectrometry. So as the name implies, we use here the inductively coupled plasma in the mass spectrometry. Sorry about that. And here are we get the final results and discussion. And the first point is yield of the tungsten during the sample dissolution, and we are going to discuss here about yield. The following sample dissolution procedure outlined the experiment section. A large amount of fluoride deposition remained after the 20 ml, zero point 0.5 molar HCl and the 0.5 molar HF steps. In order to determine the amount of tungsten that co-precipitated with the fluorides, the results after digestion of 1 gram JB3 and 4 gram BHVO2 was spiked with an appropriate amount of 180 tungsten tracer. So 180 tungsten tracer has been calibrated against a centriprep tungsten standard. The fluoride size were then dissolved completely with this 6 molar HCl and 3% weight by volume. H3BO3 to reach spike sample in isotopic equilibration. Usually about 8 ml, 3% weight by volume H3BO3, and if about 4 ml, 6 molar HCl were required to dissolve the residual fluoride from 1 gram of basaltic sample matrix. So the part of the sample solution was diluted to 50 ml for IC inductively coupled plasma mass spectrometry analysis of some elements other than tungsten. So the remaining sample solution was evaporated to the dryness and redissolved and picked up in 50 ml, picked up about and an exchanger. Sorry about that. The remaining sample solution was evaporated to dryness, redissolved and picked up in 15 ml, 0.5 ml HCl and 0.5 ml HF, and then passed through the two-stage column separation. Ion exchange as table 1 and DODG as a table 2A. We have discussed it in the previous slides. So finally, the mixed ratio of 180 tungsten over the 184 tungsten were measured by ICAP QC ICPMS. The total tungsten from the fluoride resides were then calculated by isotopic dilution. So here is the chemical purification of tungsten. The figure is given next, and we are going to discuss the purification of tungsten. So the figure in the first step, during the sample load stage, more than 70% of matrix element in the sample solution, such as different elements that we have discussed earlier, like calcium, iron, magnesium, and sodium, chromium, etc., are directly elated first, and the remaining matrix element diluted completely with additional 30 ml, zero point 0.5 molar HF and HCl solution. So after their addition, Subsequently, the titanium, zirconium, hafnium, and tungsten can be completely striped with the 60 ml 7 molar HCl and 2 molar HF solution, and we have discussed it in the previous slides as well. And after that, if we move on to the next slide, that is about the figure 1. Here we go. So in this, first when the recovery happens at about when we load, and when the elution volume is about when the elution volume of HCl and 0.5 molar HF solution is small, and with a small amount of the diluted volume, all the results are separated out, like iron, calcium, magnesium, aluminium, and sodium, chromium, etc. All these are separated out. And if we talk about on the right section, in which the we use eluents like 7 molar HCl and 2 molar HF. So with the concentration, as the elution volume increases, as it starts from this 70 ml and it reaches about the 80 ml, zirconium and hafnium are extracted out first, and then the vanadium also going to be separated along with the titanium. But the peak for the titanium is about 85 to 90 ml of the HCl and HF solution. When when the volume of the eluents increases about uh, 80 to 85 to 90 ml, the titanium also eluted out. And at the last, when the elution volume of the eluents reaches up to 100 100 and 100 105, so the tungsten is also eluted out. And as we increase the elution volume, or the graph shows that the whole of the uh, elements are extracted out at the end as the volume increases up to the 130 ml. So this was the first figure, and previous slides depicts all about this. And in the next figure, we are going to discuss the typical elution profile. And during this, the loading for the titanium, zirconium, hafnium, and tungsten with the 5 molar 8 ml HCl and HF onto the TODG column, that is greater than 60% of titanium directly passed through the column, and the remaining titanium on the column could be completely removed by additional 4 washes of using HNO3 and HF solution of 3 molar, and using the 2.5 ml just. And then zirconium, hafnium, and vanadium are strongly retained on the resin under the conditions. So after the titanium elution, 90% of the tungsten could be recovered by 5 washes. Now by using 3 molar 3 ml HNO3 and 5% H2O2, we got 90% of tungsten after the elution of titanium. And after the vanadium, when the tungsten is eluted, 95% of the zirconium hafnium could be striped with the 4 washes of 2.5 ml 3 molar HNO3. So 90% of tungsten can be eluted out by using 3 ml 3 molar HNO3 and 5% H2O2 solution, and more than 95% of zirconium hafnium combination can be eluted out by using 2.5 ml of 3 molar HNO3 and 1 molar HF solution. So consequently, an elution scheme that is given in the previous table 2A are also adopted for the primary TODGA, titanium, zirconium, hafnium and tungsten separation. So here is overall graph that we have discussed earlier, and it depicts that as the elution volume increases at load, as we load with the 8 molar HCl and 0.01 molar HF, the titanium starts eluting, and its recovery decreases down, and at the load point titanium eluted out first, and as the eluents uh, mm, eluents mixture HNO3 and HF is increases, the whole titanium is extracted out, and then when we use 3 molar HNO3 and 5% H2O2 solution as eluent, the vanadium is extracted out at about 20 ml of elution, and finally it is almost all eluted out at 35 ml. And in the next section on the right side, as the volume of the eluent, we use here the elution eluent, and that is 3 molar HNO3 and 1 molar HF, and when the amount is going to be increased from 35 to 40, the zirconium first eluted out, zirconium and hafnium along with both are eluted out, and the whole amount of zirconium and hafnium is eluted at about by increasing the volume up to the 55 ml of the eluent. And in the last figure, that is about the polyprep column packed with the 0.3 ml 50 to 100 micrometer TODG resin was adopted for the second stage tungsten purification, as we have done with the tungsten purification by the first two figures, and so the final purification can be done with the polyprep column, and in the and this can be adopted with the second stage, and this can be called as the second stage of vanadium purification for the sample mass that is greater than 1 gram. After a number of tests, we use 8 molar HCl and 0.1 molar HF for the sample loading, and further the elution impurities such as minor residual like titanium and vanadium tungsten are eluted out by different molarity HNO and HF solution. So the elution curve are shown in the figure 3, that is going to be on the next slide. And first, in that after sample loading, the 2 ml 8 molar HCl and HF solution, the additional 4 washes of 2 ml HCl and HF solution will get out about 98% of titanium, and that remain with the tungsten was removed. And after that, titanium elution close to about 100% of tungsten can be directly recovered in the 3 washes by using 2 ml 3 molar HNO 3 and 1 molar HF solution. Consequently, an elution protocol are shown in the table to be as implied, as we have discussed in the previous. Are employed for the secondary TODGA column purification. So here is the overall figure that depicts the elution curve for titanium, zirconium, hafnium and tungsten for 3.3 molar TODGA column. And it also depicts exactly right about about the uh, right like the previous slides figures, and in this we got almost all the remaining purification, remaining titanium and tungsten uh, remained in the previous first two steps. So all this will be eluted out by using first HCl and HF solution, and increasing the volume. First, the titanium will be eluted out by using the elegant HCl and HF, and then by using HNO3, 3 molar and 1 molar HF solution, we can extract it out all the tungsten from the mixture, and in this we will extract it out all the titanium and tungsten from the mixture. So here is the advantage for the TOTG scheme over the previous method. As first, the method is highly efficient for titanium and vanadium separation, and after sample loading, the titanium can be completely removed by uh, 10 ml of 3 molar HNO3 and 0.01 molar HF solution. So secondly, the method is highly efficient for the removal of zirconium hafnium from the tungsten. And third advantage is specific TODGA method is not sensitive to the resin volume. The molarity of 3 molar HNO and 8 molar HCl and the concentration of 5% volume by volume H2O2 in the element. So in this specific TODGA is not sensitive to the resin volume. This is really good for this method. And finally, this two-step TODGA separation procedure is quite rapid, and rapidity is not in the previous method. So TODGA scheme is more can be, you can say, advanced than the previous one. So here is the conclusion of the whole scenario. A novel two-stage chromatographic method for the tungsten separation from the large mass of mafic rock that contains 1 gram, more than 1 gram, for the ultra high precision isotopic analysis has been developed. First, the titanium, zirconium, hafnium, and tungsten are separated collectively from the sample matrix through an ion exchanger chromatographic method. So first we eluted all these four elements, and subsequently tungsten is rapidly separated from the titanium and mixture of zirconium and hafnium with high purity by two-step TODG extraction, as we have mentioned previous in the previous slides. So the total yield of tungsten during the two-stage chromatography operation steps, like ion exchanger plus TODG, is greater than 90%. Along with these two 90%, and compared to the previous published method, this newly TODG method has a great advantage, particularly the extremely high efficiency for the titanium and tungsten separation. So that's end. Thank you so much.